Hello and welcome again to my Physics Online video lecture supplement series. Today's video I'm going to be continuing my set of lectures number 2 for Physics 1 courses, which is a set of lectures on kinematics in 1D. Specifically, today I wanted to talk about motion with a constant acceleration. So in the previous lecture set, we considered a few of the terms that were involved in kinematics. Namely the displacement, the velocity, the acceleration, and the scalar equivalents to each of these, which would be, for example, distance or speed or the magnitude of the acceleration. And I suppose I should throw in there also the actual position, which is kind of hidden in this displacement, right? Displacement's a change in position, so you have to have position in order to have a change in position. So we considered all of those in the first part. Today, what we're going to do a little bit more of is trying to link these together using a specific parameter, namely time, that is shared between these equations. And so if you have a constant acceleration, it's relatively easy to solve for let's say the position as a function of time, given the acceleration and given an initial position and an initial velocity, etc. In fact, you can do it algebraically. If you have a non-constant acceleration, then there's sort of two things that can happen. One is you can look and see, is the acceleration approximately constant? Can it be approximated as a series of constant accelerations? In other words, is it what might be called a quasi-constant acceleration? Or alternatively, if it's a nice, smooth, continuous function, then you would need to use calculus in order to solve for the set of equations. So in any case, regardless of whether the acceleration is constant or not, you need to have a few of the initial conditions given in order to complete the picture. Specifically, for each one dimension that you're looking at a motion in, you need one set of equations and you need one set of initial conditions. So at this point, we're just still looking at what might be called linear motion or 1D motion. So this means that we will be trying to obtain one set of equations to go with that. So before we look at constant acceleration in general, I wanted to start with what happens when you have constant velocity. So if you have constant velocity, the implication is that the acceleration is actually zero. So this is a special case of constant acceleration motion, by the way, because the acceleration is in fact constant, it just has a constant value of zero. So what happens in this case is that you have an instantaneous velocity which is equal at all times to the average velocity. And that in turn is equal to the slope of the position versus time graph. So if you have a graph of position versus time with a constant velocity, you would expect to get a straight line. This equation right here actually describes the position versus time. It is basically the position is the velocity times the time plus the initial position. And since the instantaneous velocity at any time is equal to the average velocity, we can rewrite it as average velocity times time plus instantaneous position. So this graph, again, if you were going to graph x versus t, you can see that you're going to get a straight line, and you can see that the slope is going to give you the velocity. And if you were then to make a graph of, let's say, velocity versus time, you'd get a horizontal line, which therefore has a slope of 0, which matches with the fact that the acceleration has a value of 0 at all times. So that is the simplest condition. Well, maybe it's the second simplest condition. I think the simplest condition is velocity is 0, acceleration is 0. Both of those are constant. The thing just sits there. but that's kind of boring. At least in physics terms, it can be kind of boring. So the next simplest then is the constant velocity, and then after that maybe something like a semi-constant velocity or a quasi-constant velocity. So I've put up a couple graphs here that would be an example of a semi-constant velocity. So here you have a position versus time. The position is increasing linearly, then at some point in time it is decreasing linearly. Basically it goes somewhere, turns around, comes back. This could be called a semi-constant velocity because you'll notice that during either one part of this motion, the velocity is in fact constant. And so how you might analyze this is you'd have an equation that looks like the one on the previous slide for this motion. And so you'd be able to write something like x equals v1 times t if this is part 1 of the motion. So this has velocity v1, or maybe 12 meters per second, or I guess on this 12 kilometers per hour. And then for part 2 of the motion, you have a velocity of maybe negative 12 kilometers per hour and is also constant. And the way that you might put together this equation is that you'd do something like this. So you see I've labeled these part 1 and part 2. You'd have something like x is equal to v1, which is the velocity for part 1, times the time, plus the x initial for part 1, which as you can see is actually 0. So in this particular case it's 0. And then maybe like a comma, t is less than whatever time this occurs at. I guess say 0.25 hours. So 15 minutes or whatever you want to write here. And then for part 2, you would have to use x is equal to v2 times t plus x initial in part 2. And that is again for at least for t is greater than 0.25 hours. And this right here would be sort of like a t prime. Now what you would write down here in your notes then is that t prime is really t minus 0.25 hours, because that was the end time of this first part of the motion. And then you'd have a second thing, which is you'd have to solve for what is the position at the start of this. And so x initial 2 is equivalent to x1, or x of t equals 0.25 hours, which, reading off from this thing right here, you have a position of about 3 kilometers. So 3 kilometers is what you'd put here. And so this right here, this term becomes 3 kilometers. And so that's basically how you might model this. Alright, so now that we've done this almost simplest case, we can look at the slightly less simple case in which you have a constant non-zero acceleration. And so recall that the acceleration is the change in velocity per unit time. So instantaneous acceleration is equal to the average acceleration in the event that you have constant acceleration. And so what that ends up leading to is that you have a velocity versus time equation that looks like this: v equals at plus v initial. So the question becomes, what does position versus time end up looking like? Now note, by the way, that this velocity versus time, if you were to graph this, v versus t, a is constant, this is constant, you'd have a straight line whose slope is a, whose intercept is v initial. So what we're interested in now is, what does position versus time look like? And the answer is that if you have a constant acceleration, the implication is that the velocity is either going to be uniformly increasing or it's going to be uniformly decreasing with time, and linearly so. So we can make a nice approximation for the average velocity, and it turns out, by the way, that this is not just an approximation, it is a true average velocity, which is that you can use this sort of arithmetic average of initial velocity and velocity at time t to give you the average velocity for the interval whose duration is t. And so basically what that is that we're saying that the average velocity is v plus v initial over 2. So that's the average velocity from 0 to t. So then that can be substituted back into the position versus time equation. So what would that look like? Recall that our position versus time equation looks like this. X equals average velocity times time plus x initial. And this is true regardless of whether the velocity is constant, regardless of whether the acceleration is constant. This is in fact a true definition for the average velocity. If you want to find the average velocity, what you do is you take the change in position, or in other words x minus x initial, and you divide it by the time that change in position took. That is a definition, so this is true regardless of what is happening with the acceleration. Alright, but now we have this other equation that says that the average velocity is the velocity plus the initial velocity over 2. So what we're going to do is we're going to substitute this into our position versus time equation for the average velocity. So what that means is that x should look like v plus v initial over 2 times time plus x initial. Now with that said, we just wrote down that for constant acceleration, v is equal to the acceleration times the time plus the initial velocity. So we can substitute this into the equation that we just obtained for this term right here, the velocity term. So that means that now we have x is equal to the acceleration times the time plus the initial velocity plus the initial velocity again, all divided by 2, and all of that is times time and then plus an x initial. Now what I want to do is group like terms. So we have a v initial, we have a v initial, so we can kind of scribble that out and put 2 v initial. And similarly, we have this at plus 2v initial over 2. We could just as easily change that into a fraction that looks like this, a times t over 2 plus 2v initial over 2. So we might as well just cancel out these two 2's. And what this ends up giving us is we can multiply both terms by t. You end up getting that the position x is a over 2 times t, so 1/2 a times t squared, plus v initial times t, so the initial velocity times the time, plus the initial position. And that is your position versus time under the condition of constant acceleration. So again, here is your position versus time for constant acceleration. And remember again that the assumption in this equation is that we have a constant acceleration. If the acceleration is not constant, then this equation is no longer valid. When you have a constant acceleration, and when you have a motion in one dimension, you can actually relate the distance traveled to the acceleration and to the initial and final speeds. you end up with an equation that looks somewhat like this. And where this equation comes from is that you can solve the velocity versus time equation for time and then substitute that back in to the position versus time equation, and then sort of cancel or add together like terms, combine like terms. And what you end up getting is an equation that says that 2 times the magnitude of the acceleration times the distance traveled should be the difference of the squares of the final speed minus the initial speed. So it turns out that you don't need to know the time in order to know how far something has traveled, as long as you know what the final speed is, what the initial speed is, and what the acceleration is. And if you have semi-constant velocity, if you have semi-constant acceleration, then you can also obtain all these equations that we've been doing piecemeal, just like what we did with semi-constant velocity. In other words, you look at each piece of the motion. So, for example, maybe you have a motion that has an acceleration that looks like this. Then you can look at the first time interval where you have a constant acceleration, and then the final conditions of this interval become the initial conditions of this interval, and now you have a constant acceleration. Final conditions here become initial conditions here, and actually you have constant velocity, but you have zero acceleration. And then final condition here is initial condition here, and so on. There's a second type, by the way, of what I'd like to call quasi-constant acceleration, which is shown actually in this first graph. What you have here is a graph in which you wouldn't say that the acceleration here is constant per se, but it does very nicely approximate a single horizontal line. In other words, it wavers a little bit, but that ripple is much less than the difference between this horizontal line and zero. So in this case, you might be able to approximate the motion, especially over long time intervals, large time intervals, as if this had a constant acceleration which was equal to the average value of the acceleration during this rippling motion. Okay, so now I wanted to look at a special case of constant acceleration, which is called freefall motion. So freefall motion basically means you have an object which is falling under the influence of only one thing, which is gravity. So air resistance is negligible, or the object is in vacuum. In other words, there's no air to produce air resistance, and it is in fact falling. It's not being held by a hand or a string or a magnet or whatever you want to hold the object with. It does not matter for this kind of motion whether we're talking about an object that has been tossed straight up into the air, whether it has been dropped, whether it has been thrown straight down. The only thing that any of these do is affect the initial speed. They have no effect on the acceleration. So the initial speed is determined by, is the object thrown or is it dropped? The initial velocity is determined by, is the object thrown upward or downward, and how fast is it thrown at? Or if it is dropped, then that's equivalent to initial speed being zero. There's actually a famous experiment that was conducted for this, in which a hammer and a feather were dropped, and in fact they did go to the moon for one of the Apollo missions and drop both a hammer and a feather on the surface of the moon, and they dropped them from the same height, and by actually dropping both as opposed to throwing both end up hitting the surface of the moon at the same time. You don't have to go to the moon in order to do this experiment, though, because we can of course create a vacuum here on Earth, and so you can set up a vacuum chamber and drop a hammer and drop a feather next to each other, and they will both hit the ground at the same time. Most of our freefall problems will tend to take place near the surface of the Earth, and so the freefall acceleration near the surface of the Earth is given by about 9.8 meters per second squared. And so unless otherwise stated, this is the value that is being used to calculate acceleration due to gravity in free fall. If you go to some other planet or moon, then you're going to get a different value for this gravitational acceleration. We usually use a lowercase g to represent free fall acceleration, and in particular to represent gravitational acceleration near the Earth's surface. So instead of using an a in the equations that we've been discussing, we replace the a with a g. And if you go to different locations around the Earth's surface, you actually get slightly different values for g. So 9.80 meters per second squared might be the gravitational acceleration if you're standing on the ground in, let's say, San Francisco, near sea level at a reasonable latitude, and so on. If you were to go up into a very tall mountain or into a very deep canyon in the ocean, or if you were to go to the equator or to the North Pole, the value of g does change very slightly, and we'll discuss why that is in a future lecture. The actual value usually changes by as much as plus or minus maybe 0.02 if you're terrestrial. If you go into outer space, then it can go to 0, and if you go to, for example, the moon, it might be 1.67 meters per second squared. On Mars, it's about a third of the factor, a factor of 1/3 of this acceleration, and so on. And the other note of convention is that if we call up the positive direction, then that means that gravitational acceleration is usually a negative vector because it is downward towards the center of the planet. And again, the acceleration is constant when in free fall. So that means that velocity is not constant. It can in fact be positive or negative. The object may be speeding up, it may be slowing down, it may be momentarily stopped. And what these graphs right here are showing is an example of what the vertical position, the velocity, and the acceleration might look like as functions of time. This is an object which has been thrown upward into the air. It may have been thrown straight up. It may have been thrown with a horizontal component to the initial velocity, because remember, looking at these axes, the x-axis is always time. This is basically saying that the object goes up, 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 reaches some peak height, and then is coming down, down, down. And this one specifically maybe is showing that the person throwing it was standing up on top of the roof of a house or a short ledge on a cliff or something, because the final position ends up being about 6 meters below the initial position. If you look at the velocity versus time, you see that it's initially traveling upward with the fastest speed. It is finally traveling downward with the fastest speed. And then at the point in time at which you reach the maximum, at the point in time at which you return to the 0 position is the point in time at which the velocity should be the negative of the initial velocity. And here's the acceleration versus time. It is constant. On this graph, it looks like it says -10. You probably can't really distinguish between -10 and -9.8 because that's about a 2% difference, and the scale is just a little bit too thick in order to see that. In any case, there's a few things that are interesting that you can do with free fall. One of them is that you can figure out what the total hang time of an object is. So this is basically a how long is the object going to be in the air for. So you begin with your basic kinematics equations under constant acceleration. So you have v equals a times t plus v initial. In other words, speed is the acceleration times time plus the initial speed, or you can do this with velocity. And then what happens is you want to solve this equation for time. And so in doing that, you have v minus v initial over a gives the time. So final speed minus initial speed divided by acceleration is the time. And the thing to note about this is that when the object is at its maximum height, you also have a speed of 0. The algebraic argument is, and it's sort of the physically what's happening argument is, if the object has non-zero speed, then it is either traveling upward, I should say non-zero velocity in the vertical direction. The object is either traveling upward, in which case it's going to be higher in just a moment than what it is now, or it is traveling downward, in which case just a moment ago it was higher up than what it is now. So either way, you have to have a velocity of 0 in order to be at the maximum height, or a vertical component of velocity equal to 0 to be at the maximum vertical height. What this means is that if you want to find the time at which the object is at its maximum height, which I'm labeling T max here, what you do is you take the magnitude of the initial vertical velocity and you divide it by the magnitude of the acceleration, which, since it's in free fall, should be g. Alright, now if you want to get the total hang time, it kind of depends upon what the conditions are. If you are throwing the object from the ground and it's going to land back on the ground, in other words, this is a symmetric motion, object lands at the same height that it left at, then it should take the same amount of time to get from the bottom to the top as it takes to get from the top back to the bottom. And so that means that you can take that maximum time that we solved for in the previous step, multiply by 2, and now you have the hang time. If you're throwing this off of a cliff, or alternatively if you're on the ground and you're throwing it up into the air so it lands on top of a cliff or ledge or whatever, you no longer have that symmetry. And so what you have to do is you now have to solve for t by using this equation. This equation again is the kinematics under constant acceleration equation. What you do is you have a final height. So maybe if you're standing on the ground and you're throwing the ball in like a basketball into the air to shoot like at a basketball hoop, maybe you're throwing the ball from 6 feet above the ground and the hoop is 10 feet above the ground, then your y final is 10 feet and your y initial would be 6 feet. And in order to solve this equation, because you have an initial non-zero velocity and an initial non-zero acceleration, you have to use the quadratic formula. So this is the quadratic formula for solving for the value of x for an equation that says ax squared plus bx plus c equals 0. So really what you're solving for in this equation is the time t. So you'd say something like t is equal to negative v initial plus or minus square root of v initial squared minus 4 times this difference between y final and y initial times 1/2 of the acceleration, and then you divide that by 2 times half of the acceleration. So I hope it's not too confusing that we have a lowercase a in both equations to represent a different thing. In any case, once you've done this, you've mathematically solved for what times the ball will be at what you've defined as the ground level. It turns out that this plus or minus means you're going to have 2 different solutions. And so what that in turn means is you have to then use some physics to figure out which of the 2 is correct. So for example, if you throw a ball off of a cliff from a height, let's say 30 meters above the ground, and you want to know when will the ball be 32 meters above the ground, you'll get two different times. One of those times is when the ball is on its way up and first passes through the 32-meter height. The other time is when has the ball first fallen back to 32 meters. So you have to use some physics to figure out which one of those two you're actually solving for. The other thing that you might solve for in a free fall problem is the total height attained. And basically the total height attained is going to be solved for using some combination of these equations that you have. So you want to get the actual position at the maximum height. So maybe you know what the time is at which it's a maximum height because you did that in a previous step. So you could plug into this equation and get what the height is at that point. You can also try to figure out what the change in height is using the time-free kinematics equation, namely that the final speed is 0, and so 2 times a times delta y, or 2 times g times delta y, should be negative v initial squared. And if you want to get the actual maximum height, well, delta y is that maximum height minus the initial height. So rearrange the equation to solve. So I wanted to basically conclude this lecture with a kind of long example. And so this example basically says that you are in your friend's Jeep. You're driving around at a speed of about 30 meters per second. This is a, kind of a highway speed around these parts. And it's night, and so a deer jumps into the road 200 meters in front of you. You see the deer, your friend sees the deer, your friend slams on the brakes because he doesn't want to hit the deer. The deer does what deer always do, it just stands there staring at you while all this happens. And let's say that your friend is able to get a deceleration of 2 meters per second squared constant. So assuming that it takes about a half second for your friend to see the deer and register that it's there and then slam on the brake from this time where the deer is 200 meters in front of you, assuming that that has happened, what we want to know is, are you going to stop in time or are you going to hit the deer? So I've arranged the information given in the problem here, and what this is basically a sort of semi-constant acceleration problem, right? You have one portion of the problem in which your acceleration is 0, and that happens for half a second, and then you have one part where you're slowing down at 2 meters per second squared, or negative 2.0 meters per second squared of acceleration. So the first thing maybe to do is figure out just what happens in those 0.5 seconds. So for a equals 0, what you end up having is that the change in position is given by v initial times time. And so that basically is going to be 30.0 meters per second times half a second, or in other words 15 meters. All right, so this delta x equals 200 meters. We could, by the way, write x initial equals 0 and x final must be less than or equal to 200 meters to not hit the deer. So what we've basically done here is this delta x is going to affect what your conditions are for the start of the constant acceleration problem. This right here basically becomes x initial for the second part of the motion, so x initial 2. All right, so second part of the motion, now you have x is equal to 1/2 a, we could call this a2 if you'd like, t2 squared, or t prime squared, whatever you want to call it. plus v initial 2 plus x initial 2. All right, so t2 could be from t equals 0.5 seconds on. We could say that this right here starts at 0 when t is at 0.5 seconds. Doesn't really matter either way. And so the question basically becomes when v final, which is equal to the acceleration times the time minus the initial speed, plus the initial speed, when this is equal to 0, where will this be? So we can solve this for time and then substitute into this. Alternatively, we can use that 2 times the acceleration during this interval must be the final speed squared minus the initial speed squared. So both of these should give us the same answer. And if we do it this way, basically we have 185 meters left, right? 200 meters minus 15 meters. We have 185 meters left to not hit the deer. So this is less than or equal to 185 or hit. All right, so let's solve this for delta x2. So delta x2 becomes v final squared minus v initial squared over 2a2, and v final squared needs to be 0 because you've got to be no longer moving. So this becomes negative of 30.0 meters per second squared divided by 2 times negative 2.00 meters per second squared. So plugging these guys into our calculator, I obtain that delta x for this interval is 225 meters. So the implication is that you do hit the deer. Hit deer. Because you needed another 45 meters in order to stop correctly. Excuse me, you need another 40 meters to stop correctly. In other words, reach 0 velocity here. So unfortunately you hit the deer. The good news is that you may or may not be hitting it particularly fast at the point when you hit the deer, so maybe you hit the deer and it limps off. You can calculate what the speed will be if you so desire. You basically can go to these equations and basically calculate what the time is to travel 185 meters and then solve for the speed, or you could go to this equation and figure out what the speed is by using v final squared is 2a2 delta x2 plus v initial squared, where this number right here maybe is delta x2 prime is that 185 meters you actually have to stop in. So if you do that, what you end up getting a final speed of about 12.6 meters per second, which is actually still pretty fast. You know, you're going pretty close to 30 miles per hour. So hopefully the deer gets out of the way. So maybe the deer can follow the advice in the picture given and run away. Alright, I wanted to do a second example before calling it quits on this lecture set. And so this one is a freefall motion example. So you have the San Antonio Spurs player Tony Parker, and he's attempting to make a layup against Warriors. And so somehow he is trying to avoid some people who are guarding the rim. Maybe he releases the ball on the way down, such that the height at which the ball is actually released from is 2.05 meters, and it's given an initial upward velocity of 5 meters per second. So what we want to know is, when is it that the ball is actually going to pass through the hoop, which is at a height of 3.05 meters. To solve this question, I've written out the relevant information here, And so you have your initial speed, you have your acceleration, you have the initial and final heights. And from the initial and final heights, you can therefore also get the change in height. So it's 1 meter that needs to be the change in height. And so what we do is we set up our initial equation, which is the position versus time equation. And we're basically trying to solve for the t squared. So we might want to rewrite this equation as a quadratic. So you have 1/2 at squared plus v initial t minus delta y, where delta y is the difference between y final and y initial. So because this is a quadratic equation, we're going to use the quadratic formula to solve for the time t. And so that looks like this in terms of the acceleration and the initial speed and the change in height. So you can plug in the numbers from above into that equation. You get something like this. And when you solve for the time, what you end up getting is one of 2 times. It's either taking 0.273 seconds or 0.747 seconds. So the question is, which of these two is the answer? And to get the answer, we use a little bit of physics. So what happens to the ball? It is being thrown up from a height of 2.05 meters. It is trying to make it into a hoop whose height is 3.05 meters. And to do that, what happens is that the ball basically hits an apex and then passes back through the hoop. So it passes through 3.05 meters twice. Once on the way up, which is this one, and then once on the way down, which is this one. And the one where it's actually going through the hoop is the one in which it is on its way down. So this right here, the 0.747 seconds is our actual answer. So it should take a little under 3/4 of a second from when he releases the ball until when it passes through the hoop, which is just a little outside of this picture. So that is it for today's lecture. The sources that I have used, mostly for images, but also for a little bit of inspiration and problems and double checking, that kind of thing, are listed here. The main ones, of course, are the OpenStax College Physics text, the OpenStax University Physics text, but also I resort to the web to find some of these images. So that's it for today. I hope that you enjoyed today's video, and thanks for watching.